Welcome to this ATA Insights webinar. Thank you for your ongoing interest and support of our webinar program. Today's session will begin in 2 minutes. ATA Insights Webinars is an online platform for the dissemination of professional renewable energy knowledge across international borders. Our aim is to democratize access to information, for innovation to spread faster, and to make the industry more competitive. And we do this through our online sessions, open to all our members. Every year we do more than 100 sessions with over 250 speakers, 50,000 attendees from more than 50 countries. To participate in the session today, use the chat on the right-hand side to introduce yourself, your company, and where you're joining from. Under the screen, you will find the Q&A box, where you can send your questions for the speakers. We will get to as many as we can today. We're recording this session, and we will send you a link to the materials in a few days. Please consider supporting our content creation for the webinar program. Contact us on the email on screen. So good afternoon, good morning, ladies and gentlemen, and welcome to this online session. We will be talking about one of my best favorite topics, which is CSP, concentrated solar power. All of you that know me from a long time know that this is one of the topics that have galvanized my career into solar energy, and I have some good friends that have been there along all these years, including one person who is with me today, Mark Mijos. I'll introduce you guys shortly, and then some new friends also that are coming to the CSP arena. Welcome, guys. You've been working on it for a while, but also welcome, and welcome everyone also in the audience. So what are we going to talk about? We're going to talk about CSP simulators and how we can optimize from design to operation using these tools today. Before we start, I'd just like to ask my colleagues, my panelists today, to introduce themselves so that you can know them a little bit better. Mark, I'll start with you. Please, if you could introduce yourself.
Yes, thank you, Belen, and we have known each other for a long time. Yes, my name is Mark Mijos. I manage the Concentrating Solar Power Program at the National Renewable Energy Laboratory here in Golden, Colorado, and I'm also the Thermal Energy Sciences Group Leader at NREL.
Thank you very much. If you're in CSP and you don't know Mark, you've done something wrong. Go back, because I'm sure that most people know him already. Next, I'd like to ask Patricia to please introduce yourself.
Hi, good afternoon from Spain. Thank you for being here. My name is Patricia. I am from Tenatom. I'm the head of the simulation solution. And my life, all my professional life is linked to simulators. I was in charge of a full scope simulator and was responsible of its good performance. And I'm let's say expert in operation, especially in nuclear, but little by little, I enjoy this work. Thank you.
Excellent. Thank you very much, Patricia, and welcome. And of course, Guillermo, please, if you could introduce yourself.
Yes, sure. Hello, everyone. This is Guillermo Garcia speaking from Spain. I am currently the head of the process engineering within Abengoa Energy. Well, in the past, I participated in the construction, engineering and construction of many of these concentrated solar power plants in the past, not only in Abengoa, but also in previous companies. So pleased to be here.
Thank you very much, Guillermo. So for the people there in the audience, just a few things. Of course, we've prepared and we have 3 presentations from Mark, Patricia, and Guillermo. But then we're going to have the option for you to send questions, and we'll hopefully get some answers from these experts. Rarely ever you have the opportunity to ask questions from people who with such expanding knowledge on the topic. So I animate you and I ask you to please send your questions through so that we can actually get a chance to get to them. I'm going to ask Mark if you could prepare your screen so that you're ready for your presentation. And just a few things, guys, to send your highs, and I already saw that some people like Gonzalo Martin has already said hi. Send your hi, this is me, this is from where I'm connecting, there on the right-hand side. And for your Q&A at the bottom, please. And if you're in YouTube, because I know that some people are on YouTube, please also send them in the comments. And our colleague Valeria, who is in the back there, but is paying attention, she will pick them up and also leave them in the chat for us so that we can answer it. That's one. And second, enjoy this webinar. CSP is making a comeback in a big way. We've heard news of it in China. We are hoping very soon for a tender in Spain, and in Chile we've seen record prices. So this is the beginning. I mean, the real impact that CSP can have on the grid, in a decarbonized grid, is really about to become a huge point. So this is why we all now look at this topic today. So Mark, go right ahead, please.
Okay, and you can see my screen, correct?
Yes, we can see it perfectly. Thank you very much, Mark.
Okay, great. Thank you and good morning, I guess here in the US, good afternoon in other places. Again, my name is Mark Mijos, and I was asked to provide an introduction to the best practices study. And within that study, which was very broad, I'll provide some perspectives and key findings related to simulation, CSP simulations or CSP modeling. Let's see if I can advance. Okay, so over the next 10 minutes or so, I'll provide a brief introduction to the study. I'll give my perspectives on simulation models. Why are they important? Where are they important? Who are they important to? And then I'll provide some guidance on best practices for these models. So for brief introduction to the best practices study, about 2 years ago now, it seems like yesterday, but it was a while ago, we released this study with the objective of identifying best practices, identifying and publishing best practices for a whole audience of stakeholders, including engineering, procurement, construction, commissioning, all the way through operation and maintenance of both parabolic troughs and receiver plants. And the point, again, was to try to help these stakeholders avoid some of the problems that hindered, especially some of the early projects under development in CSP. The audience was everybody involved in CSP. Again, developers, investors, lenders, EPCs, again, all the way through operation and maintenance of these plants. And in some cases where, frankly, we didn't necessarily identify a best practices, are there R&D activities that could benefit reliability of these systems? So I had a broad team, and you may know many of these people, a lot of these people. Belen knows everybody. These people have been around for a long time. So I was the principal investigator on the study, but we worked closely, NREL worked closely with Solar Dynamics, Hank, Dave Kearney, Fred Morris, Bob Cable, Greg Cole, just a great group of people. This project was funded by the Department of Energy Solar Energy Technologies Office, but we did receive quite a bit of cost share and collaboration from these entities. And I'll talk about everybody else later, but the World Bank, Solar Paces, Stella and EPRI, the US Electric Power Research Institute. So a lot of support from those folks. So thanks to them for that. So that was a very quick background. Now I'll talk about some perspectives on CSP simulation models. So why are they important? Well, there was a study conducted by actually my task. I'm the operating agent for Task 1 Solar Thermal Systems within Solar Paces. But DLR, Tobias Hirsch, actually led a study back in 2011, first looking at what the yield assessment impacts of all phases of a project development cycle. And they published a study, it's here at the bottom, called the Solar Paces Guideline for Bankable Solar Thermal Electric Yield Assessment. It was revised back in 2017, but they did a nice job talking about all the phases of project development and the importance of modeling within those phases. And modeling impacts everything from the preliminary macroeconomics to pre-feasibility, feasibility studies, the development, the commissioning, and then eventually, again, operation of the plant. And as you go through each of those stages, the importance and the uncertainty of that modeling ideally decreases over time. The importance increases, but the uncertainty decreases over time. And I'll talk a little bit more about that later. So where are these performance models important? Well, I think this is pretty obvious, but they're important everywhere in the system. You have to have an accurate performance model of the entire system. And these systems are very complex, everywhere from the solar resource input to the solar field, whether it's a parabolic trough field or a heliostat field, but all the way through the rest of the system. There are some subsystems that are maybe more important than others. And we focus a lot on these in our best practices report. And again, I'll talk about this a little bit more later. Okay, to whom are these solar simulations important? Well, they're important to everybody. And I alluded to this earlier. I mean, the developers, the investors, the lenders early on in the project, the generation off-takers, all the EPC firms who are building this project, the vendors, the operators, the policymakers. It's important to everybody involved in a CSP project. I hope the presenters later will speak towards some of this. Okay, so best practices for CSP simulation models. So to understand the best practices, we talked to the universe of CSP stakeholders out there. And this is a list of pretty much everybody we talked to. And I think you'd recognize most or all of these names. US participants, European participants, participants from China, kind of everybody. It was a great project, lasted about a year and a half to do all of the interviews and feedback that we received. We also visited a number of plants. We visited parabolic trough plants throughout Spain, also in the United States, also in Morocco. And then, of course, of the limited number of central receiver plants, we pretty much visited them all, apart from those that were in China. So we had a lot of discussions, a lot of good tours, and I think we came out with a good product. So the product, I mean, this is basically the report structure. And again, this did not focus entirely on modeling. Obviously, we had an executive summary where you can find a couple of points on modeling. Then we really dug deeply into the project organization and implementation, project execution, O&M. Then we focused specifically on the trough technology and the molten salt technology. But there was not one place where performance models were discussed. It was really discussed throughout, which made this presentation a little bit hard. So I'll focus on a couple of key points, but read the report because it's buried throughout. Okay, so on the performance model, let me just list out a few points. And I've highlighted some areas in red that I think are particularly important. But as I mentioned earlier, all CSP projects rely on a performance model throughout the various phases of project development. One important finding was that the industry needs independently validated performance models. And I'll talk a little bit about how those are validated in a little bit. But those models are used for performance guarantees and for eventually evaluating the ongoing performance of the plant. This is extremely important. These models need to be able to accurately model the transients of the plant, the daily startups, the shutdowns, cloud transients. Next slide, I'll talk about how often they need to, how high resolution you need to model that at. So I alluded to this earlier, but the DLR-led Solar PACES study did attempt to do this validation. They did look at 9 operating parabolic plants throughout the world. They looked at a number of models compared against the output of the generation of those plants. And what they found is the output of that model relative to the predicted generation of those plants or actual generation of those plants could vary by 33% between all of the models. That's a huge difference. I wouldn't call it an uncertainty. It's just a bias in some of the models, which I guess is an uncertainty. But for those models that were validated against existing plants, then those models only differed by 6%, plus or minus 6%. Huge drop in the uncertainty of that model. So validation is key. So subsequently, and again, it's listed here at the bottom, on the Solar PACES side under task 1, or just go to this link here, Solar PACES DLR used some of that information, but developed a very robust guideline for best practices for yield assessment for both CSP and tower plants. And I highly encourage you to look at that if you haven't already. I suspect you have. Okay, the other important aspect of modeling is solar resource input. So that we found that the estimation of the DNI, the direct normal insolation resource, is one of the biggest sources of uncertainty for modeling the projected annual power yield or daily power yield. So many of the early projects, not so much today, I don't think, but the early projects made their annual performance forecast based on hourly data. And hourly time series do not accurately account for the transient behavior of that plant. As I described earlier, you have to have something higher resolution than those hourly models. And what we found, and what people are doing, I should say, are looking at much higher time resolutions, 10 minutes, 10 minutes, 15 minutes. But in some parts of the plant, like the receiver, maybe you need actually down to 1 minute data, maybe even less, to understand those transients. Very important. Another interesting observation was the difference between the actual and the expected site radiation. Even if you're measuring site radiation at those high resolutions, it doesn't mean you're going to capture the impact of those transients. I mean, there are other unexpected transients, right? You have short-term clouds, you have jet contrails. We see those a lot in California, unfortunately. And those impact operator decisions, especially operator decisions when they want to be very conservative. You know, you model a plant and you model your plant based on relatively aggressive assumptions. Well, operators don't like to operate aggressively, maybe appropriately so. So you have to take that into account. So again, that's a high-level summary of some of the key points in this report, but it's buried everywhere in this report. So please download it and please read it. There's a lot more than modeling. Again, it covers kind of everything related to best practices of CSP technology. I don't necessarily need to read this, but I'll close with this. I talked about modeling. That's what I was asked to talk about. But we did talk about kind of everything related to CSP, these plants. And generally, we find, and we're seeing, that if CSP developers and operators, EPCs, follow their best practices, not ours, I mean, we just reported what they are doing, then we do think that future tower and trough plants, you know, can be built on time, they can be built within budget, and they can perform as expected. Thank you.
Thank you very much, Mark. Thank you very much. I know it's been difficult for you because it was such a wide study with a different wrangling altogether, but you've made an effort for us to bring this topic forward. So we thank you for it. And I add to Mark also my recommendation that you read this study. I do know all of the authors personally. I was there when you guys were gathering the data and when you, I mean, I wasn't there all the time, but I've met you several times throughout, and I know how much care has been put into all of those conclusions there. So I think it's like a must. You must read it if you're in this industry. It's not an option that you have to read it or not to read it, because it will give you the basis, the standards that all of us should follow in order for the projects, you know, to work appropriately. I'm going to ask you to stop sharing, if you may, Mark. Yeah, perfect. So thank you very much, Mark. And now we're going to the next presentation. Patricia, please, if you get your screen ready, and don't be shy, guys, because I can see that you're getting shy on me. Don't be shy, send your questions, you know. I can see a few of them coming through, but we do have time for more. So Patricia, we can see your screen perfectly. Can you take the mute of your microphone? It's at the top. Or let me see if I can ask you to unmute. Yeah, okay.
Okay.
Go ahead then. Yeah.
Can you hear me?
Yes.
Okay, thank you very much. Okay. Well, let me make a brief introduction about Tecnatom, just a brief overview, okay, because I know that Tecnatom is not a very common company in the CSP projects, okay, but after this webinar, I think you are going to know about us a little bit more. Okay, we are a high-tech engineering company that for more than 60 years has been supporting the industrial facilities and power plants, accompanying them throughout their life cycle. Our mission is to make, to ensure the safe, the efficient and excellent operation of power and industrial plants. And we are an international group. We have a global footprint, and we have run more than run projects in more than 40 countries, and we are certified by customers and organisms in more than 30 countries. Our our primary activities are related with inspection, structural integrity services, training based on simulators, and plant operation support engineering. Okay, we were born to provide support to the Spanish nuclear sector, but over the last decade we have moved on. We have diversified our products and services into the international market, and now we are supporting not only nuclear sector but also renewables, combined cycle power plants, coal power plants, and we have been in the industrial sector, in covering oil and gas, manufacturing, process industry, aerospace, railway, and automotive. Okay, regarding the simulation area, we in the last decade we have developed more than 40 simulators worldwide. From different kind of technologies: nuclear, conventional, thermal, power plants, combined cycles, and also for aviation. Okay. Well, we have been digitalizing the processes after that the concept or in 4.0 industry was born. We were focused on engineering simulators and staff training simulators. We are not only developers, we also exploit and maintain full scope simulators, and we maintain in accordance with the international standards. We have developed our own technology that make us independent from third parties. We have developed our own configuration management system, and of course our own methodology in order to develop simulators. Okay. Well, we cover not only the simulator development, we also give consulting services. For example, if you are thinking about a technical specification of a simulator in your project and you don't have idea, we can support you, no matter if we develop later the simulator or not, for example. We also operate the simulators, as I said before. We also give training. It's not only to have the machine, it's also to drive it. And we have a very high skilled instructors. And of course, very important, is not only to have from the beginning a good simulator. The key point here is to maintain it during the life cycle of the plant, to maintain it updated and keep the fidelity of this simulator according with the evolution of the plant. Okay, and why we are here? Okay, a couple of years in Madrid took place a conference about CSP projects, and here the National Renewable Energy Lab presented a study that Mark has already talked about, in which they speak about the best practices. And our surprise was that some of these good practices and recommendations was already implemented in another generation technologies, for example, in nuclear power plants or even in combined cycles. Additionally, we have several references in the CSP projects, and that is why is Guillermo here today with us. We have been collaborating with Abengoa in several projects, giving support to their designs with simulation. So our objective here today is to disseminate the contribution of simulation in the CSP projects. What I'm going to try to do today is to make clear our three-phase simulator concept. Here you can see how a simulator can evolve in a natural way from engineering simulator till a full scope simulator for training. We have mainly 3 phases. In the first phase, we can support the design or detail engineering based on dynamic models. After that, we can move to a second phase in which we can implement the logic and control. We can stimulate or emulate or even simulate the logic and control. We can integrate in a simulation platform and animate the logic and control to check it, to debug the mistakes that could be from the engineering, and to redefine or fine tuning the logic and control. We also can use this simulation platform to make the system commissioning, to integrate all the pieces, all the components, all the systems all together, and to test it in a very dynamic way. We also support the operating procedures in this phase. And after that, once the plant is in operation, we collect the real data from the plant, and we make a review, an as-built review of the simulator in order to make it as real as the plant, to make its performance as close as the reality. Sorry. Okay, but what is a Tecnatom simulator? Because people tend to speak about or think that a simulator is a distributed control system animated. For us, it's not a simulator. This is a part of a simulator. For us, of course, the distributed control system has an important part, but it's something else. We have high fidelity models, thermohydraulic dynamics models that covers the system of the plant. We also have what we call Meteo, our solar field and radiation model, in which we simulate clouds and winds, okay? And we also integrate the human-machine interface. All these parts are integrated in a real-time simulator in order to guarantee that the response of the simulator is good enough. Okay, and we have at the top, you can see the instructor station from where we can control the session. We can load different initial conditions. We can introduce malfunction, not only related with instrumentation and control, but also with pipe breaks or tooth breaks, I don't know, filter fouling, or for example, a pump trip, or even a turbine trip. And in addition, we can simulate also the variability of the grid. That is what we call simulator. And here you can see a generic simulator. Generic means that it's not a specific plant. Okay, it's our own simulator. Okay, here we are disconnecting the plant from the grid. You can see how the generation switch is open, and you can see how the plant is evolving. Okay, the steam that doesn't go to the turbine is going to it has to go to the bypass, let's say, and you can see how the system is moving or is acting automatically according to the logic that is programmed. Okay, some valves are closing and others are opening and are controlling. Okay, and you can see how the temperatures, pressures are evolving. Okay. Of course, we also have the alarms. Okay. And if we continue with NREL recommendations, if we are in the design phase, here we can see how simulation can contribute in this stage of the projects. Okay, and NREL says that the plants and equipment must be designed for the transient behavior. Okay, the design, the technology issues that were founded in the study are actually design issues that can be solved by appropriate engineering equipment selection. And EPCs should continue to improve designs and equipment selection based on experience and operational plans and careful technology innovation. Okay, well, we can say that simulation is a technology innovation. It's another way of doing the things. We can support engineering and equipment selection based on those dynamic models. We are, of course, independent. We are no EPCs, or we are not a final owner. So we can support these kind of projects with independent verification based on that dynamics models. So finally we can prevent the engineering unforeseens and regarding with equipment sizing or transient, and covering that lack of expertise or sometimes of guidelines. In the design phase as well, we in REL recommend us to pay more attention to the control systems and automation of the plants. As I said before, integrate the logic and control in advance. In a simulator or in a simulated environment, give us a lot of advantages in order to detect the logic and control mistakes, in order to remake it, in order to check as well how to manage the alarms. That sometimes is not a good point. There are a lot of them, or sometimes there is a lack of them. So in this case, we can prove or test in advance in a dynamic environment, in a dynamic simulation. So we can see what is going to happen in the reality. And once again, we can prevent the unforeseens related with instrumentation and control and the HMI. We also support the very correct design of the HMI to make the work of the operator a little bit easier. Okay, more regarding the design. Okay, as Mark said before, the industry needs the use of performance models that cover transient behavior, the startups, shutdowns, clouds. And this is more than an animated DCS, okay? This is a full scope simulator that covers, as we say, transient different operative conditions, malfunctions. What is happening if my controller is failing? So we need this kind of tools, okay? So, and once again, we are independent from the EPC or owner, so we can support them, but we can give with our experiments, with our simulators, another point of view. Okay, regarding the commissioning. Okay, here we use what we call the virtual commissioning. The virtual commissioning is a very useful tool in order to, and it's a very good practice. It's very useful because in another sector is trendy, let's say, and it allows us to reduce the commissioning times, cost, by minimizing those unforeseen events. And of course, it prevents the risk on the real components, okay? Because sometimes you don't know how it's going to be the test. But if you try it in advance, you test in advance your procedure or your maneuvers, you can train it, and at the end, the component is going to be better than if you do it completely blind, let's say. So here we can use also the platform, the simulator, sorry, as a platform in order to integrate all the systems, all the components that the EPC used to divide among a lot of actors, no, you can use those design information and integrate little by little in our full scope simulator. Additionally, in this commissioning phase, we can use the simulator not only for engineering purposes, but also for training in an initial stage. We can use the platform to work together with EPC, with the final OMM team, and to integrate a multidisciplinary team. We also use the simulators to validate the procedures, okay? And as I said before, you can try in advance, you can test it in advance without risking the real components. And of course, we use the simulator to cover also of designs cases test, okay? Okay, regarding the operation and maintenance phase, here in Royal recommend us to have a well-trained operation team, okay? They point out that it's necessary to have a rigorous and continuous training. And if it is possible, it's very nice to have a training simulator. Okay, here, our experience is that in this phase of the projects, it's very important to master the transient and emergency scenarios, not only the normal operation, and also, as you say, the transients with clouds. But another point important is to train the manual maneuvers, okay? But sometimes the plants are very automated, and this is a good point. But what happens is if a controller fails, well, the operator has to maintain the skills to operate in a manual way if it is needed. So it is very important to train in advance in a simulator just in case. According EPRI study, more or less the 20% of the trips of power plants are linked to human errors. Imagine if we can reduce this 20% with simulators. At the end, it increases the safety and the availability of the plant, and of course, reduce the OMM cost. Okay, at last, our conclusion is that the evolution from an engineering simulator to a training simulator is a very natural process that allows us to take full advantages of the development already carried out. A simulator can support all the life cycle of the plants, not only covering from the design till the operation, but also when plant modifications happens. We can use the simulator in the same way. If you want to try in advance one change in your plan, you can use the simulator if its scope is correct for doing that. You can do it, and in this case, you can boost also those changes. Okay, and at the end, we can say that the contributions of simulation in CSP projects are cost reductions, safety increase, availability increase. And if you think about coupling this simulator with other technologies or disciplines such as monitoring, data analytics, computerizing procedures, virtual reality, or augmented reality, we have as a result a real smart plant concept and a real digital twin. And that's all from my side.
Thank you very much, Patricia. Not little, actually. You have gone into a lot of detail. Thank you very much for the detail in every stage. You obviously took to heart, everything, all of the recommendations there. So thank you very much. There is a few questions for you. We'll get to them at the end. Take a look at them if you like for now. And Guillermo, now is your turn. If you could please share your screen. I'm going to mute you, Patricia. And give your presentation. And there are so many people in this webinar today from very many different places around the world. We are delighted to see there is so much interest from far afield, as well as from the markets that we all know, like Spain, like South Africa. It's really interesting to see that you guys are still watching out and interested in CSP. Guillermo, your presentation?
Yes, hello. Sorry, Belen, I did not prepare any
Oh, no,
presentation.
you're just talking. Perfect. Go right ahead.
I am not very good in doing presentations. I do
Go
engineering
right ahead.
much better, right? So, well, actually, Patricia invited me to join this webinar just as to brief you with my experience with the simulators Technatom did for Abengoa in the past. To my knowledge, we have procured 3 simulators to Technatom. One is for the parabolic power plant, 50 megawatt plant here in Spain, close to our head office in Sevilla. Another one was for a larger plant in South Africa, and the third one, which is the one I did participate in, was for a molten salt tower plant in Chile. Right? So I have a very good experience with that, because it's really a fantastic tool, right? Because I think that already Patricia and Mark they explain everything, but because of the nature of these plants themselves, right? You need to account for, or you need to validate your thoughts about how you're going to start up the plant, how you're going to warm the system through, how are you going to manage upset conditions, how the fluctuations are impacting the weather. There are clouds, daily start, stop. This has really impacted the behavior of the plant, but it's not only the behavior itself or the control, but it's also the output, power output you're going to get, because it is not the same when you need 2 hours or 3 hours to run your system through and start it, but if you take 20 minutes. So this is kind of pretty clear. Also, it helps you to validate your control strategy, right? Because it depends on how you do it. You can start, or you can run the plant through overnight, or you have to stop and start again. And this is impacting everything, right? And the sooner you get to know this, is the better, right? That is something I would like, because I was paying a lot of attention to the presentations before, and I think that is a kind of thing we should differentiate, is between the performance model itself, which is normally used for financing and to have some kind of idea of what would be the turnover of the plant, and the simulator. The simulator is a much more complex tool, right? Because you really can operate the plant, you can really see how the stuff is working, whether you have really sized properly equipment, and so on, right? So in my experience of what we did at that time, is that I was the lead process and mechanical engineer for such a project, and I got engaged into the simulator built up pretty soon. The process was kind of very natural, as Patricia said, is that you start sharing your PNIDs, your control logics, your data sheets for your equipment, and they build up the simulator. Later on, once they build something up, you go and test it, and you can, on one hand, confirm that what they did is what you thought, or what it was supposed to be, and on the other hand, as they already pointed out, you really check that your logic and your equipment, that everything is right. Actually, we found some issues which we could already solve straightforward, right? So there was some logic, because I think that one of the fantastic things these simulators have is that it is a dynamic tool, right? In engineering, especially in the EPC, we don't do dynamic simulations very often. It's difficult, it's costly, so we don't have such tools. We have a heat and mass balances or different load cases, something like that. Probably, I don't know, a little bit of water balance, some stuff like that, but very simple, very straightforward. So you have somehow to assume, or to, based on your experience, the more experience you have, the better you know how it works, right? But in such a project at that time, which was brand new, it was like very helpful for us to test it and to check it and to realize in advance that something was not properly thought, especially during warm-up, startup, and so on, right? So this was like very good at that time, right? It did also save a little bit of time later on for commissioning, because we had the chance to actually tune the controllers. Control loops, you know, they must be tuned, and as this is an actual simulator which is dynamically actuating, you can check and tune all these parameters, and this is something you already have for the commission, right? This is also a very good thing, right? And one of the things we wanted to do at that time, but we could not do, unfortunately, was to couple the simulator of the plant itself with the electrical system, because one of the key components for these plants, especially when they have storage, and storage pretty much in fashion, right? Because we need to be dispatchable, was exactly to check that we were really dispatchable, and that we could have a very good grid frequency control, because this is very tricky. As you may know, we are not firing gas. We don't have fast reacting equipment. These things takes time. When you have to pump 3,000 cubic meters per hour of molten salt through a receiver, this takes a little bit of time, and the electrical grid reacts very, very fast, and you need to be fast reactive, right? So this has some implications, not only from, let's say, purely control or electrical point of view, but it's also in the process, right? It has, you may need to add some more components. You may need to have a strategy to do that. And this will have definitely an impact in your revenues, right? And this is something you need to assess. So I have little more to say, because I think that my colleagues did very good presentations. Next time, I promise I will prepare some for you guys. And I can only recommend you to really invest in these tools, because they are helpful already from beginning. It's an online check which you can do of the stuff you are doing, what you are planning, what you are procuring, and it enhances the whole thing, right? So congratulations to Technaton for this product, and I think this is all I can say for the time being.
Thank you very much, Guillermo. I don't think you need a presentation. You've done a great job, and you've been very easy to follow, so don't worry about it. You don't need PPTs. You're excused from now on. Okay, so there's a lot that we got through here today. We have about 10 minutes-ish. There are some questions that are here in the waiting for answers. So I'm going to start. Patricia, get ready, because a few of these are for you. Although, you guys, if you want to add anything, Mark, Guillermo, please feel free. The first one is, I would like to ask about the operation of the parabolic through plants. Trough. My God, my brain is going already. It's too late. I would like to ask about the operation of the parabolic trough plants. Do you know if O&M companies are interested to have detailed simulators in the solar field? What benefit would the operators have with the simulator? Is it, if it's okay to share, did you provide such simulators before? So yeah, I mean, it's a good question. Once it's all built and I'm just operating the project, why do I need a simulator, essentially?
Well, according to the question, do you if there are companies interested? Yes, they are. For example, but I just wanted to know. We are focused on just the solar field, because the OMM, I think, is more interested in a full scope simulator, not only for the solar field, but the impact on this solar field simulation with the whole plant. And this is what we were talking about. We have developed trough plants, okay, and parabolic trough plants, and we make a detailed simulator solar field, okay, but well, let's say it's not is as detailed as the operator needs, okay. So when we develop a simulator, we have to make the balance, because we can do it as detailed as we want it, but we have to know what is the end use of this simulator, or what is the purpose of these simulators. So in this case, the solar field has For example, we make the model, it's a radiation model in order to simulate the clouds, okay? And when the clouds are passing, the mirrors detects that via simulation, it changes the temperatures and so on. So the operators at the end needs the solar field in order to adapt the transient regarding the clouds or regarding the wind. I don't know if I asked.
Thank you very much. I think you've answered. I don't know if you guys want to share anything. Let me know. Mark, go.
I'm thinking if I want to share. I mean, if I understood the question and the importance of understanding the dynamics in the solar field, whether it's a parabolic trough or a tower solar field, I think it's very important. In the US, we don't necessarily have the small clouds, going over the solar fields. We do, but not like you find in Spain or in some other countries where you find these small clouds flying over the solar field. I think having an accurate model of partially shaded solar fields is very important. Maybe it's more important for a heliostat field where you have an immediate impact on the receiver. Probably still very important for a parabolic trough field where it influences control of each of the individual solar loops or SCAs. So for operation, I'd say it's very important.
Yes, I would like to add something to what Mark just said, and this is
Go right ahead.
Yes, thank you. So this is that it also depends on the size of the plant, right? When you have smaller plant, and a small cloud may really have an impact. You have a very large solar field, and there are some small clouds around. You may not even notice it, but it also it is also depending on whether the steam generation, because at the very end we are heating up something with the sun, sorry, to generate the steam, and if this is done directly, coming directly from a solar field, and there is a cloud, you may have a transient which is not acceptable by the turbine, by the steam generator itself, if the gradient is too steep or whatsoever. We face even some dramatic situations with this, so this is really important. It's not that there is a cloud and then the temperature is reducing a little bit and has no impact. If your solar field is sensitive to this because you are generating steam directly, either in a central receiver without steam generation, or a small solar field which is forwarding hot HTF towards steam generator, and the temperature suddenly drops, you need to know how to react to that, because it might even cause a turbine trip, and then you need to restart the whole plant. This is an issue, and it's costing a lot of money.
Thank you very much, Guillermo. I see that you guys have been answering questions. Mark, you've answered some questions. Thank you. And also, Patricia, you've been also there, but somehow we have a bunch of questions now for the few minutes that we have. So the next question, Patricia, can you clarify what you mean by solar field radiation cloud simulating cloud events? Are these site-specific adjustments measured on typical meteorological year DNA data? It's the first one, yeah.
Yes. Our model, for example, in the simulator that I saw you in this presentation, we upload in the simulation a historic data of the meteorological conditions, the DNI, the wind, and we can collect and introduce this data in the simulator. Okay, we have the solar field simulated, and this data comes in the simulation, and the simulation just go on and continue depending from on the operative condition. I don't know if I asked him, but it considered these details. I have to say that I'm not. I have not a developer of this model. So, but if you want more information, we can give this kind of information. But
get in touch with Patricia; she'll sort you out with the right information. Patricia, just tell us which projects have you actually provide the simulators for, so that everyone knows, because there's a few questions along these lines.
Okay. Well, we can give you names because it's a good practice. So in this case, it's a good propaganda. So here we have been working for Helio Energy 1 and Dassault 1, and we have 2 replicas more in Manchasol and Estresol. We have also developed a simulator for Cachu Solar 1 in South Africa. The rest was Spanish ones. And we have partially developed a Atacama power tower.
Okay, so quite a few, because there was a question about whether Morocco, but now is answered, you guys. Okay, so I wanted, there is one more here that I'd like to ask. Let me see if I can find it. How are these improved simulators integrated with the control system of the parabolic trough plant? Does the DCS normally have an integrated simulator?
Yes, we integrated. We have several approaches to introduce the distributed control system. We can do it using a stimulation. Okay, that is the same DCS from the plant. We stimulate it. We have another option that is simulated. In both cases, it's just a integration. We have the same model of from the vendor, and we just adapt it in order to adapt in a simulation environment, because you have to think that a DCS is designed to work continuously. It is not thought to charge an initial condition, to make a backtrack, for example, so to introduce a malfunction. So we have to make little adaptations, but it's completely integrated. And we have in those cases, we were guaranteed that the DCS is exactly the same as the real one. But we have another option that is more, let's say, cheaper, that is to simulate the DCS from scratch. In those cases, we have create our translators, and we reproduce the logical control of the real DCS. In this case, the response of the control is very close to the real one, is more or less exactly the same, but the difference is the maintenance of the simulator. It's not so, let's say it's more time consuming, because it's not exactly the same, it's not the same component, and it's already updated and it comes from plant. We have to readjust with simulation engineering.
Thank you very much, guys. There is a bunch of questions more because we don't have a lot of time. If you want to take a look and you want to answer any of them, let me know. But I do have a question that is my own, actually. Mark mentioned 33% variance in simulation that they found in different projects. This is a lot. And I want to ask about how do we reduce this, because presumably the uncertainty and the risk in that is quite high. How do we make sure, that we are as accurate as possible down to the, I don't know, Mark, I'm going to open with you because you for sure they have given it a lot of thought, since you were the one that came up with the 33% in the first place, you and the team of the project. But then Guillermo, Patricia, if you want to answer any specific questions, let me know, okay? Mark, go ahead.
Okay. And I'm getting some band gap issues, so I hope you can hear me. Yeah, we've thought about it a lot. High resolution, minimum of plant output. And I know that's a hard question, but we need that data basically to true up our models, to train our models, to validate our models. As a task one operating agent in Solar PACES, that's a key activity that we're going to push for. The industry, in my opinion, needs I wish the industry would share some amount of data, even if it's anonymous. I think that would go a long way in helping the different model simulator developers to validate those models. It's huge.
Yeah, thank you very much, Mark. We'll work on that. Then we'll have to convince all of the projects that have been operating for more than a decade, to yield some data.
We have to.
If we want to survive, right, as an industry.
Yeah.
So how about you guys? Do you want to answer any specific questions? Patricia, Guillermo? Guillermo, you go first.
Well, just to to point something out from this question you just asked us, and Mark has already responded a little bit, but I think these performance models, I'm not into that at all, right? I only see the outcomes. It's always you have to generate this much power in a typical meteorological year with these operating hours and so on. And how to say that? I mean, I think that is all lies, right? Because they don't reflect the reality. They always because it must be difficult. I have to be honest. I could not do it, but you have to simulate how long does it take to warm the turbine through, how long does it take to warm a receiver, how long does it take to bring the plant to healthy conditions. So all these kind of things, and also the strategy behind it, this differs, right? So this whoever does that, it takes a lot of assumptions to make it simpler, right? It compares to whatever to be bankable. So bank trust that is right, and it may be or may not, right? So Mark was very right before saying that the only way we can get this better is when it's compared to actual plants, right? And for comparing apples to apples, you need to know not only let's say the inertia or the dynamics of such a plant, but also the strategy, how they operate. It changes a lot. It changes a lot. So this performance modeling, to whatever is related to banks and financing and all these things, this is really tricky, right? So I don't know as an industry how this should be tackled, or to be homogeneous and that we are all playing under the same rules, let's say like that, because if somebody is having a very optimistic performance model and is supposed to generate a lot of energy, which at the end of the day is not true, and whoever is financing the project is having an issue. And on the other hand, it might be the other way around, that you are too conservative, your outcome is supposed to be very bad, so nobody's going to finance your project. So it's kind of tricky, right?
Thank you very much. Very tricky, Guillermo. Yeah, and Mark, you agree with this, right?
I do. I have one other point comment to bring up, but I don't know if you have time.
No, go ahead. Yeah, after I'll give Patricia the chance.
It's a bit of a change of subject. I'm not going to talk about it really, but it's important. Somebody did ask about, how do you model seasonal changes? How do you model the grid side? We've talked about the plant side. I think it's equally important, and I would recommend you have another webinar just looking at the grid and how do you optimize these systems for the grid? How do you optimize the generation for local grid conditions? Guillermo talked a lot about dynamic effects. How do you take those into account? I'd love to see a webinar on that side of the equation.
So long as you participate, we're all good.
I'll get somebody, probably not me, but somebody. We do a lot of it, so.
Yeah, no, see, all of your latest studies, we are on them, trying to learn as well. So thank you very much, Mark. We'll take that into consideration, hopefully soon, because it's important. And I think here is the quid of what makes CSP different and more responsive to the grid and more valuable to the grids. This is a point that we honestly cannot make enough. The guys on the battery side are always like, pay me, pay me, pay me. Look at all this value. They do a great job, so we just need to do more of that. So Patricia, what about you? Any last questions you want to answer, or you want to add something to the last one, perhaps? We cannot hear you at the moment. Just make sure to take your microphone off. Yeah.
Yes. Okay, I was answering one of them, but just ask me, Belén.
No. Which one were you answering? Let's do it live.
Oh, okay. Well, I was answering that one that was for Mark and me. I don't know.
Okay, hang on. I know. It's hidden now. Let me find it. Here it is. Are the simulators able to study seasonal operation energy yields, considering, for example, the regional local electrical system data on demand? And so how to accomplish the plant operation storage versus system demand? So in other words, the grid side, what Mark was talking about. So go on, yeah. Please tell us.
Yeah, well, what I ask is that, yes, we can simulate whatever we want, basically. It depends on the budget, it depends on the scope you need. So it is possible. The truth is that in our projects, we have not simulate all the parts together. The demand system is not integrated yet, but we are willing to do that. Okay.
Excellent. Thank you very much. So I suppose the next stop is that we do another webinar on how to simulate the grid side of the CSP projects. Excellent. Thank you very much, Guillermo. Thank you very much, Patricia. And thank you very much, Mark, for being here with us and sharing with us. Thank you very much, everyone in the audience, for sharing and keeping the faith strong about CSP. You know, this year already we have a project in South Africa that is going ahead. Redstone, as you know, has commenced construction. We have a project in Chile that is finalized. Cerro Dominador, we have seen the cheapest ever, the bid for CSP in Chile at 3.4 or 3.39, if you like. We have seen China building a few projects, and we're hoping also for a tender in Spain. So things are moving. You know, we need more countries. You know, I saw a lot of people there from Tanzania and other countries with a lot of solar resource to look at this technology and how it can change your grid and how it can change your system. So thank you very much, all of you, and see you next time.
Thank you, Belen.
See you.
Thanks,
Bye.
everybody.